All right, let's get started. My apologies for the confusion on the wrong QR code, but ultimately I'll know who's in what class based on the timestamp. So I'll be able to sift that out pretty easily. A couple of things. So we're starting to chip away on the homework. There was a little bit of a delay that was admittedly my fault. So on homework 5.3, I had a typo on my solution. What I had done is on homework 5.3, if you look on the distributed load, it went from 300 to 450. And when I did the solution, I did 300 to 400. So my TAs said, so everybody in the class got that problem wrong, and there was probably an error with the solution. I went, yep, that was me. So I redid the solution. I'm pretty sure I uploaded the new one to Blackboard, but they were a little behind on grading. That's my fault. So they're working on that. I'm, again, still working on exam 2. My goal is to knock out both of my exams this weekend so that we can just sort of move past that, because once we get to Thanksgiving break, I can grade this one over break pretty easily, and then nothing's left but the final, so it works out pretty well. So 6.1, you all turned in, and we're doing 6.2 today. 6.2 is the second truss assignment on the method of sections, which is what we're going to talk about today. Hopefully you found the method of joints to be sort of methodical. Maybe it felt a little bit like you were solving a puzzle, you know, because that's kind of how it feels when you're doing a truss analysis. And hopefully what you found when you did the last joint is that you were only sort of solving for one member, and it sort of worked itself out. Like if you were solving for a diagonal, you could solve for the horizontal and the vertical separately, and then you check the slope ratio and you see it matches. So it's sort of like a way of self-checking the answer. But I would argue that if there's any one way of illustrating the method of joints, it's tedious and but thorough, but it does require accurate bookkeeping. Like, it's really easy to switch an arrow around and mess up your calcs. And I think that maybe one advantage of the method of sections is that you don't see that. That with the method of sections, there's very little possibility that an arrow gets flipped, if you will, because you're only looking at one cross section. Okay. Before we begin into the lecture, I guess not to mention too much of a well. Let me say two things. So first off, I had some questions from some biomedical engineering students about Engineering 216 next semester, and I just wanted to clarify that for biomedical engineers, Engineering 216 is not required. So you don't have to take that if you don't need. Break my heart, I know. But I do believe that Engineering 216 would be considered an elective in the biomedical engineering program. So that might be something to consider later. But you probably won't be taking that next semester, given that you probably got a bunch of other stuff you need to take, you know, like your A&P classes and chemistries and all that hullabaloo that you biomedicals do. So yeah, but it's a great class. Hopefully I get to see you in there one day. We have a lot of fun in there, even if it is at 8 a.m., you know. Okay, before we get into it, I guess I should mention something maybe on a little bit of a somber note. I'm sure you all saw or heard about what happened yesterday and saw the email message from the dean that came out this morning. The one thing I would mention, oh goodness, there's a lot of water spilled right here. The one thing I would mention is that one of the things that I think that's unique about engineering students at Marshall is we have a tendency to cross 3rd Avenue quite a bit, because we're going back and forth between engineering classes and math classes. So please be careful. Watch yourself on 3rd Avenue. We definitely don't want something like that happening again. Okay, let's get into method of sections. That's a typo because we only had the second lecture in structural analysis, so we're not in structural analysis 3. Okay, so going back to trusses, I want to be clear that we are all in understanding of what our analytical assumptions are when we analyze trusses. You know, this is a point that I make very, very intently when I teach upper level analysis courses that, quite frankly, I really didn't emphasize during the last lecture, but I think it's kind of important. We are not analyzing trusses. We're analyzing these mathematical models that represent trusses. We assign certain assumptions and properties to these trusses that we feel not only reflect or mimic real-world behavior, but we then also construct the truss to adhere to some of these principles. We find that it works very, very well, but I think that there's a little bit of a distinction that needs to be made there, because one of the things that's challenging as an engineer is that as an engineer you do need to perform analysis of certain systems. And I don't care if we're talking about solid mechanics, beams and columns and frames and gears and machine elements and bridges and whatnot, or if it's thermal analysis or fluids analysis. We engineers do quite a lot of that. And one of the things that we have to do is make certain assumptions about the models that we're using, and we just need to make sure that we're being thorough in our understanding of our assumptions and whether or not those assumptions are appropriate for the problem at hand. For example, the assumptions that we make when we analyze trusses are that all the members are connected by frictionless joints, which basically means that there's no unintended additional forces beyond what we get from static equilibrium from our individual joint and section analyses, and that all of the loads and support reactions are applied at the joints, and at each joint the centroidal axes of each member coincide. What those two assumptions basically mean, in concert with the first one, is that all of these elements are what are called axial force members. The only forces contained inside the members are along the axis of the member, so they're either experiencing tension or compression. And the reason for that is because all the loads are applied at the joints and all the centroidal axes coincide at the joints, and there's no unintended forces from friction or anything like that. So we have a particle statics problem, so the forces are along the axes of each member. Really the kicker is, what's the magnitude? So remember, how do we define forces? Magnitude and direction. So all we really care about is the magnitude of the force inside each member, and the direction being whether or not it's tension or compression. Now, in order to go through and determine the internal forces inside these members, we have two approaches. The last lecture and the last homework assignment, we explored the first one, which is the method of joints. Again, tedious and thorough, but it works in getting the entire structure solved with relative ease. Like once you get the hang of it, you're sort of rocking and rolling with it. The method of sections is the other approach, and that's what we're going to be exploring today. The method of sections is really, really powerful if your goal is to determine forces inside a specific set of members, particularly members that are far away from let's say, support reactions or joints that are outstanding. For instance, if I had this truss here and I wanted to solve for the internal force, let's say, inside this member, well, I could solve for the reactions and then maybe solve this joint, then this joint, and then this joint. So I might have to do 3 separate joint analyses before I get the force in member AB, or after I get reactions, I could cut a section. So the way the method of section works is we take our secret weapon of structural engineering, which is the samurai sword or the lightsaber if you happen to be a sci-fi fan, and we cut right through the truss. Okay? Again, the logic behind that is if I'm sitting down on this table and one of you breaks out the samurai sword or lightsaber and cuts right through the table, I'm going to fall down. The reason I'm going to fall down is because inside the table right here, there are internal forces that are keeping the structure in equilibrium so that I don't fall down. So a section cut is an analytical tool that we can use to determine the internal forces inside these members. Now, whenever you cut a section, like we're looking at this truss right here, whenever you cut a section, let's call this line 1-1, this line right here. Whenever you cut a section, you are splitting the truss into essentially 2 separate pieces. You're literally cutting the truss sort of proverbially in half. As the analyst, it actually does not matter which side that you look at. You could cut a section and only consider the equilibrium of, let's say, the left half, or you could cut a section and only consider the equilibrium of the right half. It does not matter. The truss does not care how you do the analysis. The answer is the answer, okay? But that being said, it usually is advantageous to look one direction versus another. For example, let's take this truss and let's say I had a force applied on every one of these lower joints, like a force here, a force here, a force here, a force here, and a force here. Okay? If I cut a section, I have 2 options. I can cut a section and look to the left, cut a section and look to the right. I would argue, given the position of this section cut, it would probably be easier to cut a section and look to the left because there's just less stuff going on over there, right? I have one joint G over here versus over here on the right, I got H, I, J, K. There's a lot more loads. My equilibrium equation is going to be longer. Again, it's not going to change the answer, but that doesn't mean I need to make my own job harder. Does that make sense? Everybody okay with that? Now, as the analyst, I want to talk about this section cut, and I want to talk about it from a statics perspective. Kind of makes sense given the title of this course. So here is what happens when I cut a section and look to the left. When I cut a section and look to the left, this is the free body diagram that I would be investigating. So here's the structure. I've got reactions here, maybe loads here, and I have unknowns. How many unknowns do I have in this system? 1, 2, 3, right? Here's the thing. Do all of these forces all go through a common point like they do with a joint? Like if we're doing a joint analysis, here's the joint analysis. This force, this force, this force, this force all goes through the joint. But not the case over here, right? Over here, we have forces that are going through different points. If the method of joints is akin to a particle statics problem, this is akin to a rigid body problem, okay? So the advantage is whenever we're doing a method of sections problem, we now have 3 equations of equilibrium. All those joint analyses that you did on the last homework assignment, all you were considering is you looked at a joint and all you had was sum of forces in the x direction, sum of forces in the y direction. The only time you ever considered moments was when you were solving for the reactions. After you solved for the reactions, you never wrote a moment equation for the rest of that homework. Am I correct? Hopefully, I'm correct, you know, because that's the correct approach. But with this, we actually have that third equation at our disposal. So what that means for you as the analyst, remember when we were doing method of joints, we were limited to joints with 2 unknowns? Well, with the method of sections, we can cut a section through a region that has at most 3 unknowns. So the method of sections allows us to solve for this free body. We can actually solve for these 3 unknowns instead of just 2. Instead of 2 at a time, we can solve for 3 at a time. Again, because we now have that third equation of equilibrium at our disposal. Does that make sense? Okay. So here's the structure we're going to analyze today. We have a truss. We got a hinge reaction, roller reaction, a series of loads on it. And what we're going to do is we're going to solve for member EG, FG, and FH. So we're not interested in solving the entire truss. We're only interested in solving a specific subset, and particularly this member, and this member. So take a wild guess where we're going to cut a section. Bam, right through here, right? So we're going to cut a section, and we're going to look in one direction. I'm going to look to the left because I kind of flipped a coin before I went to class. It doesn't matter which direction we look. We can look in either direction, and we will get the same answer, okay? So let's break out the notebook. I can hit the end show button. Bless you. Okay. So here's our structure. All right. Before we break out our new approach, this method of sections, the first thing we should do, and really should be the first standard task for any structural analysis problem, is to determine the external reactions. We should determine the reactions here at support B and the reactions at support J. Now what I'm going to do is I'm going to assume that both of these vertical reactions are acting upwards. BY, JY. And for this horizontal reaction, BX, I'm going to assume it's acting to the left. Why do you think I'm assuming it's acting to the left? Well, let me ask it this way. Anybody have an idea what it is? It's 16 to the left, right? That's easy, right? If I got 16 to the right, BX is 16 to the left. And I can just look at it. So what I will do is I will say BX is 16 kips to the left. With me so far? So what I will then do is I will sum moments at B in order to determine the vertical reaction at J. So, oh, sorry. So let's sum moments at B. And so what do we got? Well, we don't need to consider the horizontal and vertical reaction that goes through B because they generate no moment about B. Do the two 28 kip loads generate moment at B? I would say so, right? Do those generate positive or negative moments about point B? What's that? Well, that depends on this, doesn't it? When we write a moment equation, we assume a direction. I'm assuming counterclockwise moments are positive. Here's point B. There's the 28 kips rotating like this around point B. Is that positive or negative rotation? That's negative rotation. So I've got negative 28 kips times what? What's the moment arm for this first 28 kip load? 8 feet. And what's the moment arm for the second one? Say it again. All right, what about the 16 kip load? Does that generate moment about point B? Somebody else, come on. I know it's Friday. What's that? Anybody, does the 16 kips generate moment about B? Oh, come on, everybody's shy. There we go. Is it generating positive or negative moments? I didn't hear that. Negative, there we go. And what's the moment arm for the 16 kip load? 10 feet. Is everybody understanding that? Is there anybody that's not? It's okay if you're not, but I got to know. Is there anything that's confusing about that? Remember, the moment arm is the distance from the line of action to the point in question, the shortest distance. So the shortest distance from that horizontal line along which 16 kips is traveling to point B is 10 feet. Everybody okay with that? Now, what about JY? Is JY generating moment about B? Yes. Positive or negative? Here's point B, here's J, rotating this way. We said that's positive. Positive JY times what moment arm? Come on, help me out. There we go. What's that? What'd you say? I'm getting left out again, aren't I? All right. Okay. So let's do some math here. So what do we got? 28 times 8 is 224. That's 672. That's 160. So 224, 672, and 160. Add that up, and we got 1056 or negative 1056 foot kips equals negative JY times 32, or JY is positive 33 kips. So if I sum forces then in the y direction, because that's my remaining equation of equilibrium, I have by plus jy minus 28 is 0. So just subtract that out. And 56 minus 33 is 23. And there we go. Let's box these reactions. All right. I'm going to give you a sec to catch up, but I want to see if this makes sense because y'all are being kind of quiet. And I want to make sure that, I mean, if I'm boring you, then that's a good thing. That means you understand. But if there's something you don't understand, don't hesitate, okay? Remember what I said at the beginning. Whether it's scholarships, loans, your parents, grants, what have you, somebody putting cash money on the table for you to be in this room. If there's something you don't understand, you let me know. Everybody good? Okay. Do I need to stay up here for a little bit, or are you good? Okay. All right. So here's the structure, okay? And let's write down my reactions so that I have these. So this is 33 kips. This is 23 kips. And this is 16 kips. Now what we're interested in, and I'll sort of use my highlighter here, we're interested in these three members. The problem said that we wanted to determine the internal axial force in these three members. Now, the method of section states that we can cut a section through no more than three unknowns. Since those are the members, they're all unknown, and there are three of them, I'm just going to cut a vertical section right through this series of members. And just like a CAD drawing, where you have section views, I'll call this like section 1-1. Or you could call it section AA, however you reference it in Engineering 102 or CE 102. Now, whenever you cut a section, analytically, you need to cut a section and look either to the left or to the right. I honestly don't think it really matters with this problem because we have three loads on either end of the section, so that's why I sort of flipped the coin and looked to the left. So we're going to cut a section and look to the left. So I'm going to redraw the system to the left of that section cut. And I'm going to kind of draw it a little big so that we all kind of see what we're doing. So we'll say method of sections. Cutting a vertical section looking left. Okay. So here's this, here's this, here's this, 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 this. So just so you're kind of following along with what I'm drawing here, that's 16 kips, 23 kips, 28 kips. And then what we did is we sort of cut the structure like this. So imagine, this is where we made our samurai sword or lightsaber cut. So maybe what I'll do is do that. Now, what I'm also going to do is, just for reference for what we're going to do here in a little bit, I'm going to sort of like draw a shadow of what the structure would look like if it continued out here. But again, all we're considering is this component of the free body diagram. And to put some dimensions on this, this dimension here is 10 feet. And these dimensions here are 8 feet. So one disadvantage to the method of sections, you have to do a lot of drawing. There's a lot of figures that you have to prepare, and prepare correctly. Now, the other thing I will do is label these so that we all know what we're looking at here. Okay. Now what I'm going to do is illustrate my unknown forces, okay? Maybe what I'll do is be color coordinated, and I'll say my reactions at this point are known. This is 23 kips, and this is 16 kips. I know these, so I'll say those are red because they're known, and I'll use blue for my unknowns. Now, there are 3 unknowns. What I tend to do when I'm first learning how to do a method of sections analysis is I draw all of the forces, all of them, in tension, okay? So what we'll do for this first one, we'll say, okay, I have a force here. We'll call it FEG, and I'm drawing it in tension. So tension is away from the joint, okay? Likewise for this FH, we're going to draw that in tension, yanking away from the joint. Okay? Now for this diagonal, what I'm going to do is instead of drawing a diagonal force, I'm going to say, you know what? Let's do this. And remember, these diagonals are at, here, I can do that to a little bit better scale. That's a little better. All right, an 8 to 10 slope ratio. Okay, is this okay? Does this make sense, what I'm doing here? Hopefully this isn't that complicated. Let me move this a little up, because I want to have some room here. Okay, I'll give you a sec on this because I know there's some folks who are still drawing, so take your time. Get some coffee. Now, this is the free body diagram that we need to analyze. This is the structure about which we need to determine our unknown forces. How many unknown horizontal components do we have in this free body? Unknown horizontal components? 3. How many unknown vertical components do we have? So what do you think we ought to do first? Sum forces in the y direction. Let's do that. Let's see what we get. So we sum forces in the y direction. So we have 23 acting up, positive, minus 28 acting downward, plus FGY acting upward is 0. We don't consider the other forces on the truss because we're not looking at the truss. We're looking at a section of the truss, okay? So we only consider the forces on this section, okay, which is 23, the negative 28, and the FFGY. So what is FGY? Like if you have 23 minus 28 plus x equals 0, what's x? Say it again. There you go. And it's not like, is it 5? No, it's 5. Confidence. Hold on. 5 kips up. I didn't mean to erase that. Okay. Is everybody okay with this? I mean, again, everybody's being kind of quiet. I want to make sure that you're understanding this. Everybody good? Okay. All right. So you tell me, what do you think we ought to do next? Going back to the method of joints analysis. Yes, sir?
Try to solve for FGX.
Exactly. It's exactly right. Whenever you have one component of a diagonal, do the other one. Okay? And I'm going to give you a simpler way of dealing with it as well. I mean, after the method of joints analysis, I'm hoping that this analogy will be a little easier to swallow. So slope ratio. What do I mean by that? I propose that FGX is to 8 as I can do better than that. FGY is to 10. Bless you. So I propose that the X component is to 8 as the Y component is to 10. Because what's going to happen is whenever I solve for the X component, the way that I'm going to solve for that is I'm going to say that FFGX is FFGY times 8 over 10. And this 8 over 10 suspiciously looks like I'm taking the legs of two triangles and dividing them, kind of like a trig function, right? Kind of like an opposite over adjacent sort of deal. And so what is that going to be? What is 8/10 of 5? 4. And what direction is that 4 kips going to be acting? Make sure we're paying attention. To the right. Because it's positive, we got a positive answer for this, which means our tensile assumption was correct, which means this tensile assumption is correct. So if we have FGX and FGY, how are we going to determine FG? The Pythagorean theorem. So we can go ahead and do that now if we'd like. We don't have to, but we can. What did that pop up for? So therefore, and so we'll put that over here. Hold on, let me move this. I want this to not get in the way of some of the other stuff I'm going to do. Can somebody give me an answer on this? We'll say like 2 decimal places. What is FFG? 6.40. Do I have a second on that? There we go. And what did we say? Tension or compression? Tension. One loud voice. Tension. There we go. Now that's one of them, but we got 2 more. What are our remaining unknowns? Right? Let's go to our free body diagram. Maybe what we could do is to make this a little easier. Maybe we say that, okay, that's 4 and that's 5. So we've solved for those 2 unknowns, but we got these horizontals. Should we sum forces in the x direction, what are we going to find? Well, we're going to find 16 to the left, 4 to the right, EG to the right, and FH to the right. It's not going to tell us what EG and FH are. It's just going to tell us that whatever those 2 are, they have to add up to be 12, right? We got 16 one way, 4 the other. But what was the whole point of using the method of sections? What does the method of sections afford us the ability to do that the method of joints does not? Like what do we get by doing the method of sections? We get another tool at our disposal. What is that tool? Sum of moments. We get to sum moments. So maybe what we ought to do is sum moments. Now, where do we sum moments? Now, that's the kicker. Remember, it's the same story as before. Whenever we're summing moments, I tend to want to sum moments wherever a bunch of forces are intersecting so that I don't have to deal with them, okay? And I propose that there are two very ideal locations to sum moments. One of them is F, because not only does FH go through the point F, but so does that diagonal. And if F is an ideal location about which to sum moments, I want to make sure everybody's paying attention. Where's the other most ideal location to sum moments? G. That's exactly right. Because both F and G not only eliminate one of our unknowns, but they also eliminate that diagonal, so we don't have to deal with it. What I'm going to do is I'm going to sum moments about point F, okay? You could very easily sum moments about point G, it doesn't matter, but I'm going to sum moments about point F, okay? Now, forgive me, I'm going to cut off this 28 kips. Just remember it's there. I'm going to try and not do the scrolling dance too much. But let's handle this like we would any other problem. Question. This 16 kip reaction over here at point B, that's 16 kips to the left. Do we need to consider that when we sum moments at F? Why? It goes right through F. What about the 23 kips? You bet. Positive or negative moment? Negative moment. How far from F?
16.
There you go. All right. Now we've got the 28 kips, which I know I kind of cut off. That's going to generate positive moment 8 feet away, because remember it's right there at point C. That's the 28 kips. So 28 kips times 8 feet, generating positive moment. What's the remaining force left? What's the other one I have to consider? FEG. Now FEG, is that generating positive or negative moment? There you go. Times 10 feet. Not too bad, right? So now we got a pretty simple problem. 23 times 16, negative 368. So this is foot kips. Plus 28 times 8, that's 224. Equals FEG times 10 feet. And so 368 and 224, we're taking the difference of them because that's negative, is going to give you negative and so therefore FEG is negative 14.4 kips. In this case, 14.4 kips in what direction?
Right.
Say it again. Hold on. What direction did we assume FEG was acting? And what did we get? A negative answer. Doesn't mean we need to develop significant emotional distress. Just means it's acting to the left. But from a context perspective, if we assumed that it was to the right and it's acting to the left, what does that also mean in terms of our answer for FEG? There we go. FEG is 14.4 kips in compression. Because here's the thing. whether that force is acting to the right or acting to the left is a function of how we analyzed the problem. In other words, whether we cut a section and look to the left or cut a section and look to the right, that doesn't matter. What matters is whether or not the element is experiencing tension or compression. That's what matters, okay? So what I don't want to see at the end of a truss analysis, if we're looking at internal axial forces, that the force in member AB is 20 kips to the right. I don't care if it's to the right or to the left. That doesn't matter. What matters is tension or compression. That's what matters, okay? Because again, the only reason that it's acting, let's say, to the left is because we cut a section to look this way. If I cut a section to look this way, it's going to be to the right. So, does that idea make sense? Okay. So, if that's the case, now what's left? What do we have to do to finish this problem out? And how do we do that? Some forces in the x direction. Oh. So I'm going to scroll up. My apologies for the scroll dance. But 16's negative, and we've got these three forces acting to the right. I'm going to just treat them all as positive, and then I'll just plug in a negative number for EG. If you want to, like, if you need to redo the diagram, that's fine. I don't care. I just need you to get the right answer at the end. So what we'll do is we'll say negative 16 kips, and we'll say plus FEH plus FFH, plus FEG plus FFGX is 0. Then we'll say negative 16 kips plus FFH. And then the EG was negative, so we'll say minus 14.4. But the FGX was positive, so we'll say plus 4. Again, you do it however you want. Just make sure that you're accounting for everything appropriately. And when it's all said and done, you should get I'll put it down here. FFH is positive 26.4 kips or 26.4 kips to the right. Because look at the equation, right? There's a bunch of negative numbers, just this little positive number. We got to have a big positive number here for that to be 0. So, I mean, you can check it out. That and that's 30.4. 30.4 minus that's 26.4. So if that's positive, that means that FH 26.4 kips in tension. That's it. That's the method of sections. Again, I think the method of sections, like from a implementation standpoint, maybe the downside is you got to draw more figures. But I think maybe the upside is that since you're only looking at a few members, there's much less risk that you're going to like get some arrows flipped when you're going from joint to joint. There's no joints. There's just the sections. So yeah, does that make sense? Are there any questions about this or this? I mean, you're going to have a homework problem that's going to be very similar to this. It's just going to be another truss, and I'm not going to have you solve the whole thing. In fact, I think on that homework problem, I'm only asking for 2 members. You're going to have to cut a section through 3 members, but I only care about 2 of them. So, sound good? I hope everybody has a wonderful weekend. I will see you all on Monday where we start shear and moment diagrams.